Hello, so in this video we are going to talk through the first progress test solutions. So the first question I think is a relatively straightforward question. We've been given a histogram and we've been told that the histogram here shows the height, which we're denoting by the letter H, okay, given in centimetres of a particular type of plant grown in a nursery. So you can see that along the x-axis we're talking about the height of the plant in centimetres, and it looks as if the minimum height is from 0 centimetres and the maximum height is up to 50 centimetres. And along the y-axis we've been given the frequency density. Now I'm just going to talk briefly about the difference between frequency and frequency density. So if you remember, you're probably familiar with working with bar charts, okay? In fact, a bar chart is still a type of histogram. It's the most simplest type of histogram that we can have. And the idea is that we have bars or bins, okay? And frequency is represented by those bins. In other words, the amount of objects that fall between, let's say, for example, this bin, which is 25 to 30 centimetres, the frequency will tell us how many plants are between 25 and 30 centimetres. Now, a bar chart is a situation where you have equal width bins, okay? So for example, if you have all of the bins being 10 centimetres, or 5 centimetres in width, or 15 centimetres in width, then a bar chart is fine. And in which case we would put frequency along this axis up here, okay? So we can just simply read off that the height of the bar is given by how many objects fall within that bin, okay? However, a histogram is a more general bar chart where we can have different width bins, okay? So you can see here, for example, the first bin or the first bar is 10 centimetres in width from 0 to 10 centimetres. But the next bin or next bar is 15 centimetres in width. It's from 10 centimetres to 25 centimetres. And the next bar is only 5 centimetres in width. It's from 25 centimetres to 30 centimetres. So in that case, where we have a situation where we have different width bins, we need to talk about frequency density instead, okay? If you like, the frequency density is a more realistic measure, okay? It's basically a better weighting to show, well, actually, if all these bins were the same width, then that's how many objects would be in that bin, okay? That's what frequency density tells us. But we can still get the frequency from the bin, okay? So even though we got frequency density, so we can't necessarily read off, oh, right, that first bin, so that first bin here has a height of 0.5, so there's 0.5 things in that bin. That's not true, okay? That's frequency density. We can still get the frequency by working with the area, okay? So that's the reason why we've got frequency density here, because we've got different width bins. Anyway, let's have a look at the first question. So the first question says, describe the type of skew that the histogram shows. So just remember, skew is a measure of where the mean is going to lie, okay? So if you remember when we're talking through our first theme, and if you're not sure, we can go back and watch that video again for theme 1 in this module. Skew is all to do with measure of central tendency, and specifically it looks at the mean. Okay, and if you remember that the mean is always attracted towards the outliers. So let's have a look at this, okay? Would you be happy that the majority of our data kind of lies in this region here? That's where the kind of biggest area bars are. That's where the bulk of our data lies, okay? And over here, we have what are known as outliers, okay? Those are kind of the bins which have slightly lower height, slightly smaller area than the other bins, which means that there are likely to be outliers down in the red region, and the majority of our data lies in the blue region, okay? So just remember that the mean is always attracted towards these outliers, which means that the mean is going to be attracted in this direction. So I would say that the mean is probably going to be about there. Okay, but my point is that the mean is always attracted away from the bulk of our data. The bulk of our data is here, and the mean will be attracted away from that. In other words, it'll be attracted towards our outliers, okay? So because the mean is attracted towards the negative direction, towards the left, the negative direction, okay, then we're going to say that this is a type of skew. It's going to be negative skew, okay? So I'll put here negative skew, this distribution shows. All right, fine. Now let's have a look at the part 2. So calculate the number of plants that are shown in the histogram. So we need to find the total number of plants that are shown in the histogram. So this is where I'm going to make use of the fact that we have frequency density and not frequency on this y-axis. And the reason being is we have different width bins. But that's okay, okay? So I basically want to work out how many things lie in the first bin, how many things lie in the second bin, how many plants in the third, how many plants in the fourth bin, and so on and so on. So I need to work out how many plants lie in each bin, okay? Well, in order to do that, I need to look at the area. Remember that on a histogram where we have frequency density on the y-axis and not frequency, I can still get the frequency, I can still get the number of objects that lie in each bin by looking at the area. So let's first of all calculate the area of the first bin, okay? So the first bin goes from 0 to 10, so my base is 10, okay? And my height is 0.5, so it's going to be 10 times by 0.5. So my first bin has an area of 5, which means that there are 5 plants which lie in my first bin, okay? So I'm going to write that down. So my first bin, I'm going to have 0.5 times 10, which is going to be 5, okay? So this is my area down here, okay? So that's my first bin. Let's do the same thing for my second bin. So my second bin has a width of 15, so it's going to be 15 times by my height of my second bin, which is going to be 1, okay? So it's going to be 1 times 15, so fairly obviously in that case it's just going to be 15. So there's going to be 15 things in the second bin. Alright, let's have a look at the next bin then. Let's have a look at the third bin, okay? Well, the third bin has a width of 5, okay? So the width is 5, and the height is 3, okay? So it's going to be 3 times 5, which of course is given by 15, okay? So let's work with the next bin. So the next bin over here is again a width of 5, so the width is 5 again. And the height this time is equal to 5. So the height of the bin is 5. So it's going to be 5 times 5. There's 25 things in the next bin. All right, let's have a look at the next bin. So the next bin again has a width of 5. So it's going to be 5 times something, okay? And the height in this case is 6, okay? It's got a height of 6 from there to there. Okay, so in that case, in that bin, there are going to be 30 plants, okay? Having a look at the final bin then, so the final bin has a width of 10, so it's going to be 10 times something, and the height, well, let's have a look at the height. The height is going to be 5.5, okay, so it's going to be 5.5 times by 10, which is going to be 55, okay, so there's 55 objects which lie in that last bin. So to work out the total number of plants that are shown in the histogram, I just need to add all the numbers in the second column together, okay, so the second row together. So if I add all those together, by my kind of working, it should be equal to 145 if I've worked that out properly, okay, so the answer should be 145, okay. Now, finally, we need to tick the modal interval. So just remember, the modal interval is just the interval that has the most things in. Modal, mode, most things, okay? So I just need to tick the interval which has the most number of plants in, okay? So let's have a look, and I'm going to make use of this table which I did in the last part, okay? And I'm just going to read off, well, which one has the most number, which one has the highest frequency. Okay, so the highest frequency in this case is 55, which corresponds to the last bin, okay, and that last bin is between 40 and 50, okay, so 40 less than 50, so 40 less than or equal to H, less than or equal to 50, so it's going to be that interval there, okay. Okay, fine, let's have a look at the next question then. So question 2, we have a bias coin and it's tossed 20 times. The probability of obtaining a heads is 0.3. What is the expected number of heads? Now let's write down a little bit of details here. Would you be happy that we have a coin, okay? And we're looking at the probability of obtaining a head. So that's what we've been given, the probability of obtaining a heads. And we're tossing this coin about, we're tossing this coin 20 times. So are you happy that this coin can either result in a success or a failure? In this case, my success is a heads. So I'm going to write this down. I'm going to let the random variable x represent the number of heads, the number of successes, which is the number of heads. And are you happy that because it can result in either a success or a failure, it's a binomial situation? So I'm going to say x is distributed using a binomial distribution. And remember the two parameters of my binomial distribution. First parameter is n, it's the number of times I'm doing this trial. So in this case, I'm tossing it 20 times. That's given to me in the question. The next parameter is p, which is the probability of success. In this case, the probability of obtaining a heads is 0.3. So I'm going to write 0.3 as my second parameter. Okay. So if I'm looking for the expected number of heads, I'm looking for the expected value from x, which is the number of heads. Okay. So to work out the expectation of a binomial distribution, remember, you just need to take the number of trials and multiply by the probability of success, so n times p. So in this case, n is equal to 20, p is equal to 0.3, so 20 times by 0.3 should give me 6. So I'm expecting that in 20 trials with a probability of success of 0.3, I'm expecting 6 successes, 6 heads. Okay. Now I'm looking for part 2, the probability of obtaining exactly 8 heads. So I'm going to write it like this. What's the probability that x, remember that x is the number of heads, okay? What's the probability that x is equal to 8, is exactly equal to 8, okay? Well, in this case, I can just use my probability mass function. So remember, my probability mass function for a binomial distribution should be n choose r, where n is the number of objects and r is the number of successes I'm interested in. So, sorry, n is the number of trials, okay, and r is the number of successes I'm interested in. So in this case, the number of trials is 20, and the number of successes I'm interested in is equal to 8. So it's going to be 20 choose 8. Then I need to multiply that by the probability of success, which in this case is 0.3. There's a 0.3 chance of getting a head, so we're told that in the question, to the power of the number of successes I want. So in this case, the number of successes I want is 8. Then I need to multiply that by the number of failures. So in this case, the probability of a failure is 0.7, because I'm 30% chance of success, 70% chance of failure. To the power of however many failures I'm expecting in 20 trials. Well, if I'm after 8 successes and there's 20 trials, then I'm expecting, or I want 12 of those things to be failures, okay? So I stick all of that into a calculator, I get myself 0.1144. I'm going to leave that as a probability, as a percentage, okay? So I think that makes a little bit more sense. So it's about 11.5%, 11.44% is the probability that in 20 tosses of this coin, with a probability of success of 0.3, I should expect the probability of getting 8 successes with those parameters is about 11% of the time, okay? All right, let's have a look at question 3. So we have a machine and it occasionally produces defective components. So defective just means it's not up to standards, okay? It is known that the machine produces defective components at a rate of 3 per day, okay? So if I define my random variable as x, okay, and if I say it's the number of defective components, so I just put number of defective components, so number of defective, but remember that I need to define how many it's talking about. So in this case, it's 3 per day. So my time interval is a day, okay? And in this case, okay, let's just think about this. It has to be a Poisson distribution because it's happening at a constant rate. We're told that it happens at a rate of 3 per day. Of course, we can assume all the other sort of restrictions of a Poisson distribution, such as independent time intervals and things like that, and it's discrete. But I can basically say then, if I'm assuming it's a Poisson distribution, that x is distributed using a Poisson distribution, and remember the parameter is lambda, which is the rate of success. Okay, so the rate of success in this case is equal to 3. Okay, fantastic. All right, so now we need to find the probability that in any given 5-day week. Oh, that's different, okay? Because remember that this situation up here, we were talking about in 1 day, okay? So in a day. That's the definition of my random variable x. So I need to define a new random variable then. So I guess I'm just going to call it y, okay? So y is the number of defective components. So I'll just put number of defective, okay? But instead of talking in a day like x was, I need to change it to talk about the time interval that I'm looking at here in the question, which is in a 5-day week, okay? So I'm going to look at the number of defective components made in 5 days, okay? So in that case, just using what I have before, it's still going to be using a Poisson distribution. But if x was talking about 1 day, y is talking about 5 days. In other words, it's 5 times bigger. It's a random variable that has an interval which is 5 times as long, which means that my rate, which was 3 for x, gets multiplied by 5 as well, because we're talking about an interval that is 5 times longer. In other words, the rate of defective components in a 5-day week should be 15. Okay, so I need to find the probability that in any given 5-day week, the machine produces exactly 12 components that are defective. So I'm looking for the probability that Y, remember Y is talking about the number of defective components in 5-day weeks, okay? I need to find the probability that Y is equal to 12, okay? Because I'm looking for exactly 12 components. Okay, so because it's a Poisson distribution, and I'm looking for an exact probability, therefore I can use the probability mass function of a Poisson distribution. Now it's in the formula sheet if you're not sure, but it is effectively lambda, which in this case is 15, to the power of however many I'm interested in, so I'm going to call that x, which is 12, okay? So lambda to the power of x, so 15 to the power of 12, multiplied by e to the negative lambda, so e to the negative 15 in this case, all divided by x factorial, so in this case 12 factorial, okay? So if I stick all of that into a calculator, I find that comes out as 0.0829. So it's about 8.3%. Okay, so in other words, if I know that this machine is producing defective components at a rate of 3 per day, then if I'm looking at the course of a week, assuming all the restrictions of or the requirements of a Poisson distribution hold, if I'm looking at a 5-day week, I should expect that the probability of obtaining 12 components in a 5-day week for this particular machine is about 8.3%. Okay, fantastic. Let's have a look at question 4. Okay, so question 4, we have a probability distribution for the discrete random variable y, and it's shown below. So let's just remember this, okay? So because we're looking at a discrete random variable, it basically means it can only take specific outcomes, okay? Within a given interval or within a given range. And we're given the probability distribution, the probability mass function, so the probability that y is equal to any particular value, which we're giving is lowercase y. Now it's given as 3 different things, so it's a stepwise function or a piecewise function, not stepwise, piecewise function, okay? And we have 3 different situations which the probability can take. Firstly, it can take a value of 0.3. So we can end up with a probability of an outcome being 0.3 if those outcomes are 0 or 1. So that's how I want you to read that first row, okay? So basically the probability the probability is 0.3 of this, the probability of this random variable is 0.3 if the outcome is either 0 or 1. Okay, so you can see there for the set of outcomes 0 or 1, we have a probability of 0.3. The next row in the table says that the probability of an outcome is k multiplied by the outcome take away 1 if the outcome is 3 or 4. Okay, so in this case, k is a constant. K is a constant, all right? Otherwise, the value is 0. So for all other outcomes, okay, the probability of obtaining that outcome is equal to 0. Okay, so there's basically 3 values that our probability can take. All right, so it can either be 0.3 if we have a value of 0, 1 or an outcome of 0, 1. If our outcome is 3 or 4, it's equal to k times by that outcome take away 1. Otherwise, it's equal to 0. So we need to find the value of k. So I think here we can use the fact that all probabilities have to add up to 1. Okay, so that's a factor, you know, probabilities. All probabilities have to add up to 1. So let's work it through sequentially. First of all, we have the probability of this random variable is 0.3 for either outcomes which are equal to 0 or outcomes which are equal to 1. So in other words, when we add together our outcomes, if the outcome is equal to 0, okay, then the probability of obtaining that outcome is equal to 0.3. If the outcome is 1, then the probability of obtaining that outcome is also 0.3. So far, we have 0.6 as our probability when we add it together, okay? If I look at the next row in my piecewise function, okay, then I can basically say, well, look, if my outcome is equal to 3, then the probability should be k times by 3 minus 1, yeah, because my outcome is 3, so y in this case is 3. So therefore, if I take away 1 from 3, I get 2, times it by k, so the probability of obtaining that outcome should be 2k. Then also, if I look at the outcome of 4, okay, then I should end up with a probability of obtaining an outcome of 4 of 3k. You happy? Because it's just going to be sticking 4 for y into my k times by y minus 1. Okay. Otherwise, all outcomes are 0. So effectively, I've just got loads of other probabilities, but they're all 0 anyway, so I can just ignore those. Don't have to write those down. Now, I know the fact that when I add together all of these probabilities, I should get 1. Okay, the sum of all probabilities should be equal to 1. Okay, so basically it's just a case of solving this equation. So let's have a look. So we end up with 0.3 plus 0.3, which is 0.6, 2k plus 3k, which is equal to 5k, and that should be equal to 1. So in other words, what I'm saying here is that 5k should be equal to 0.4, because of course if I take away 0.6 from both sides, okay, so I get 5k equals 0.4, which means that k should be equal to, well, 4 over 50. Are you happy? Because if I stick 0.4 divided by 5 in my calculator, I get 4 over 50. So k should be equal to 0.08 if I want to write that as a decimal. Okay, so that should basically be the value of k. Okay, 0.08. So using that fact, let's have a look at part 2. Using that fact, let's find the expectation of 3y plus 2. So first of all, in order to work with this, I need to think, well look, I know my expectation algebra. I know that this thing should be 3 times the expectation of y, add 2. Okay, what's effectively happened here is I've taken all of my outcomes, multiplied them by 3. So effectively all of my outcomes are 3 times further away from where they were before, or 3 times further away from the origin than where they were before. Okay, and then the adding 2 is effectively just a shift. Okay, it's just basically moving all of the outcomes so that they're 2 more to the right than they were before. Okay, so therefore, the expectation of y should also move in the same way. So the expectation should end up 3 times further away from the origin as it was before, and it should also be moved 2 to the right. Okay, so therefore, if I know what the expectation of my random variable y is, so if I know the expectation of this random variable, then I should just multiply by 3 and add 2, and I'll end up with the expectation of 3y plus 2. So let's first of all calculate what the expectation of y is. Okay. So just remember, it's a discrete random variable, so it's nice and easy to work out the expectation of a discrete random variable, okay? It's just simply the sum of all the outcomes times the associated probability. And again, we went through that when we looked at probability distribution. So if you're not sure where that formula comes from, go back and watch the video and it should be very clear. So what I need to do then is I need to go through all of these different outcomes that I can have, multiply them by the associated probability, and then add them all together. Okay, so the first outcome that I can have is 0. So I'm going to take my first outcome, which is 0, and times it by its associated probability. So it's going to be 0 times by my associated probability, which is 0.3. Okay. Then I need to add that to the next outcome I can have. Well, the next outcome I can have is 1. Okay, times that by its associated probability. That's also 1 times 0.3. Okay. Have a look at the other outcomes. Well, the other outcome I can have is 3. Okay. Times that by the associated probability. Well, now I know the value of k is equal to 0.8, okay? So if I stick 0.8 in here, in fact, sorry, 0.08, okay? So it's going to be 3 times by, well, if I stick 0.08 in this formula, it's going to be y minus 1, which of course is 3 minus 1, so it's 2, times by 0.08. Are you happy that's going to be 0.16 as the probability there, okay? The last outcome that I can have, which is non-zero, okay, is 4. So I'm going to take 4 times that by its associated probability. So I'm going to stick 0.08 times by 4 minus 1 as the probability. So that's going to be 3 times by 0.08. That's going to be equal to 0.24, okay? And all the other outcomes are 0 because all other outcomes are 0. So I'm basically just going to add on loads of other zeros. So if I add together all of those things, okay, then I should end up with 1.74. So that is the expectation. Okay, that's the expectation of my random variable y. So therefore, if I want expectation of not y, but the expectation of 3y plus 2, then I should just basically take 3 times the expectation of y, which I've just worked out as 1.74, and then add 2 to that, okay? So if I do that, that should come out as 7.22, okay? All right, fine, let's have a look at part 3. So very similar idea here. We now need to find the variance of 2y minus 5. So again, using my expectation algebra and variance algebra, just remember that the variance is a measure of spread. So this minus 5 in here is a shift. It's basically shifting the whole distribution to the left by 5, okay? So in which case, the spread of the distribution, the variance of the distribution, shouldn't be affected by that shift. So I don't need to worry about the minus 5, okay? But I do need to worry about the fact that all of the random variables, all the outcomes, have effectively been made 2 times further away from the origin as they were before. Okay, so therefore, because the variance is talking about the spread of the distribution, because the distribution is going to be more spread out, all the values are going to be 2 times further away from the origins they were before. Okay, and just remember that the standard deviation then will also increase by 2, but because we're talking about variance, and variance is the square of standard deviation, then the variance is going to increase by 2 squared. So in other words, this thing should just be equal to 2 squared times the variance of y. The reason why it's squared is because the standard deviation will increase by 2, the spread of the distribution will increase by 2, but because we're talking about variance, we need to talk about 2 squared, the squared of that value. Okay, so let's first of all find what the variance of y is. Very similar to how we dealt with the question, how we dealt with part 2. Okay, so let's first of all find the variance of y. Just remember, there's a few formulas that you can use. The formula that I'm going to use is the sum of y squared times the associated probability. In other words, I'm just going to square all of my outcomes times the associated probability, and then I'm going to take away the expectation, which I just found, and then square that. Okay, so that's how I could find the variance of y. Okay, so let's first of all go through, square all of the different possible outcomes, times them by the associated probability. Well, actually, I'm going to cheat slightly. I'm just simply going to use this because I know that I've got the first number as my outcome and the second number as associated probability. Okay, so all I'm just going to do is just reuse that, but I'm going to square the first number instead. So it's going to be 0 squared times by 0.3 plus 1 squared times 0.3 plus 3 squared times 0.16 plus 4 squared times 0.24, and then I need to take away the expectation of y squared. Well, my expectation of y was just 1.74, so I'm going to take that thing away squared. Okay, fine. So if I stick all of that into a calculator, I get myself 2.5524. Okay, so that's the variance of y. So therefore, I can say that the variance of 2y minus 5 should be equal to, well, it's going to be 2 squared times that variance. So it's going to be 4 times that variance, which when I stick that into a calculator, okay, comes out as 10.21. It's 10.2096. So 10.21 is fine. Okay, so hopefully that makes sense. Okay, so let's have a look at question 5. So question 5 says, a group of people consists of 5 boys and 6 girls. They stand in line for a photograph. How many ways can the photograph be taken such that boys and girls must alternate? So alternate just means it must go boy, girl, boy, girl, boy, girl. Okay, so the boys can't stand together and the girls can't stand together. Okay, so we've got 5 boys and 6 girls. Okay, so I'm going to write this down. I'm going to show you, it's not too big, so I'm going to show you how these boys and girls are going to be set up. Okay, so the boys and girls must alternate. So it's going to go boy, girl, boy, girl, boy, girl, boy, girl. So that's 1, 2, 3, 4 boys, 5 boys, girl, but I need another girl, okay? Because at the moment I've got 1, 2, 3, 4, 5 girls. Now clearly I can't put this girl on the end because then you're going to have 2 girls standing together. They must alternate. That's not allowed, okay? So I can always stick the girl at the beginning. So if I stick the girl at the beginning, it's going to go girl, boy, girl, boy, girl, boy, okay? So now all I need to do is just work out, so I know that there has to be, so if there's, well, in total 11 positions, I know that there must be a girl in the first position, boy in the second position, girl in the third position, etc. Okay? So if I just look at the positions which must have a girl standing in there, bearing in mind, or assuming that these girls can be distinguished from each other, which I presume they can, okay, they're not going to be identical twins or anything like that, okay, then because I know there must be a girl standing in each of these positions, I just need to work out how many ways I can put the 6 girls into these 6 positions, okay? So in that case, there's going to be 6 factorial ways of putting these 6 girls into the 6 positions. Similar kind of thing if I look at the positions with boys in, so these 5 positions here, okay, I know there must be a boy standing in each of these positions, and there's 5 boys, so how many ways can I put these 5 boys into these 5 positions? Well, there's going to be 5 factorial ways of putting these 5 boys into these 5 positions, okay? So in total, there's 5 factorial ways of putting the 5 boys into those positions. There's 6 factorial ways of putting the 6 girls in those positions. And of course, for every one of the ways that I can put a boy in those positions, I can put 6 factorial positions for the girls. So in other words, I'm going to multiply these 2 things together. Okay, so that should come out as, when I stick it in my calculator, as 86,400 ways. Okay, Now just bear in mind that the way that I worked that out was knowing the fact that the boys and girls must alternate. So if I just simply consider the 11 positions that I can have for the photograph, they're standing in a one-dimensional line, okay? If I just consider the positions where the girls and boys can stand at, I know that's fixed. I know that that can't change, okay? So I'll just basically say, well, how many ways are there putting the 6 girls in those positions? That's 6 factorial. How many ways are there putting the 5 boys in those positions? That's 5 factorial. Well, for every 5 factorial ways there are of arranging the boys, there's 6 factorial ways of arranging the girls. So therefore, there's 5 factorial times 6 factorial ways in total. That's going to give me my 86,400. Now, for part 2, we have a boy which joins the group. So there are now 6 boys and 6 girls, okay? How many ways can the photograph now be taken? Well, now we have a little bit of variation. So if I again consider the 12 positions, because of course there's 6 boys and 6 girls and they're standing in line for a photograph, so there's now going to be 12 positions. So I'm just going to consider the 12 positions, so where the boys and girls can stand, such that they still alternate, okay? So the first situation that I can have is this one. Okay, so you can have boy, girl, boy, girl, boy, girl, boy, girl, etc. Okay, so in other words, the 12 positions, you start with a boy, and then it goes girl, boy, girl, boy, girl. Okay, well, how many ways are there of filling this position? Well, if I just look at the girls again, okay, the girls will have to stand in these 6 positions. In other words, there's going to be 6 factorial ways of putting these 6 girls in these 6 positions. And there's also going to be 6 positions which the boys can stand in, okay? So there's going to be 6 factorial ways of putting these 6 boys into these 6 positions. However, there's 12 positions. This is the situation where there's a boy in the first position, and then it goes boy, girl, boy, girl, boy, girl, okay? But there's also the situation where there could be a girl standing in the first position, which then means in the second position there's going to be a boy, and then it's going to go boy, girl, boy, girl, boy, okay? So in other words, you could also have this situation as well. Okay, so you can also have this situation where it goes girl, boy, girl, boy, girl, boy, okay? Now again, if I just look at the girls, so the girls standing in these positions, okay, there's 6 factorial ways of putting the 6 girls in these 6 positions, okay? And likewise, if I look at the boys standing in this position, well, there's 6 factorial ways of putting the 6 boys into these 6 positions, okay? So for the first situation, okay, so for this situation where you start off with a boy and then it goes boy, girl, boy, girl, boy, girl, okay, there's 6 factorial times 6 factorial ways of getting that. So it starts off with a boy in the first position, okay. But I could also have the situation, this situation down here, whereby it starts with a girl in the first position, then goes girl, boy, girl, boy, girl, boy, okay. So again, there's going to be 6 factorial times 6 factorial ways of filling these positions, okay. So in other words, what I'm saying then is that in the first case, where it starts off with a boy in the first position, there's 6 factorial times 6 factorial ways. In the second case, where it starts off with a girl in the second position, there's 6 factorial times 6 factorial ways, okay? In which case, I'm going to need to add these 2 things together, because I can have this situation or this situation, not both. So remember, it's kind of and or. And means you multiply, which is why I'm multiplying up here and multiplying down here, okay? Or means you can have this thing happening or this thing happening, but not both, right? You can't have a boy and a girl standing in that first position. You can either have a boy standing in the first position or a girl standing in the first position. So in which case I'm going to add these 2 things together. So you could say I could do 6 factorial times 6 factorial times by 2. Either way, it comes out as a big number. It's 1,036,000 and 800 different ways of arranging these, okay? So you notice the massive difference between the situation where we just had 5 boys and 6 girls to now where we add an extra boy, okay? By adding an extra boy, we increase that massively, okay? Almost by a factor of 10. Okay, cool. Let's have a look at question 6 then. So a class of students sit a listening test and a reading test. 20% of the students passed both the listening and the reading test. So the way which we're going to interpret that is that of the students that pass the listening test, 20% go on to pass the reading test. Okay, that's what the first bit of information means. We then have the situation that 50% of students failed both the listening and the reading test. So in other words, if you fail the listening test, you go on to pass the reading test 50% of the time. It is known that 60% of students pass the listening test. Now, before I go any further with reading the question, I'm actually going to write this information down, okay? So the first situation is going to be the listening. So I'm going to do this as a tree diagram.
And the second set of branches is going to be the reading. Okay. Now let's actually fill this in. So I'm going to basically say L means that you pass the listening test, and L dash means that you fail the listening test. Okay. And then the second set of branches, so you can either go on to either pass the reading test or fail the reading test. And again, if you fail the listening test the first time round, then you can pass the reading test or either fail the reading test. So let's actually fill in the probabilities. So we're told with this first bit of information, 20% of the students pass both the listening and the reading test. In other words, if you pass the listening test, 20% of people also pass the reading test as well. Okay, which means that 80% of people go on to fail the reading test if they pass the listening test on the first go. Okay, let's have a look at the second bit of information. So the second bit of information says 50% of the students fail both the listening and the reading test. So in other words, if you fail the listening test, you've got 50% of students go on to also fail the reading test as well. Okay, fine. So in other words, that means that if you fail the listening test, there's a 50% chance that you can go on and pass the reading test. Now the last bit of information says that it's known that 60% of students pass the listening test. So in other words, there's a 60% chance of you passing the listening test, so 40% of people fail the listening test. Okay, so this is the tree diagram which I'm going to be referring to in the question. So let's go on then and let's answer the question. So the question says, what proportion of students pass the reading test? Well, are you happy there's two ways of passing the reading test? So what is the probability of passing the reading test? There's two ways of passing the reading test. You can either pass the listening test and pass the reading test. So in that case, that's going to be 60% chance of passing the listening test and a 20% chance of passing the reading test. Or the second situation you can have is if you fail the listening test, you can then go on to pass the reading test. So in other words, there's a 40% chance of failing the listening test and a 50% chance of passing the reading test in that case. Okay, so that's the reason. Okay, so just remember the reason why I multiply the probabilities together is because I want this situation and this situation. Okay, then the reason why I add these two things together, okay, so the reason why I add the two things together is because I can't have both. Okay, you can't both pass the listening test and pass the reading test and fail the listening test and pass the reading test. You can either have passed the listening test and pass the reading test, or fail the listening test and pass the reading test. You can't fail and pass a test. Okay, so if I stick that thing into a calculator, that thing should come out as 32%. Okay, so if I stick all that probability in a calculator, that comes out as 32%. Fantastic. Let's have a look at part 2. So part 2 says a student from the class is selected at random and is found to have passed the reading test. What is the probability that this student has failed the listening test? So I want to find the probability that this student has failed the listening test, so I'll put L dash for failed the listening test, given the information that they've already passed the reading test. Okay, so I've been given that fact. I've been given the fact they've passed the reading test. I want to find the probability that they've failed the listening test. Okay, so here I can just use Bayes' theorem. Okay, so Bayes' theorem says that the probability of an outcome happening given that something else already happened, so the probability that they failed the listening test given that they've already passed the reading test, should be equal to the probability that they passed the reading test given they failed the listening test multiplied by the probability of actually failing the listening test. Okay, all divided by the probability that they passed the reading test. Okay, so this is just using Bayes' theorem. If you're familiar with Bayes' theorem, in fact, it's in the formula sheet. The probability of A given B should be equal to the probability of A and B happening divided by the probability of just B happening. Okay, which you can also write as the probability of B given A happening multiply the probability of A happening, all divided by the probability of B. This is just Bayes' theorem, and we proved this in the lecture. So if you're not sure where this comes from, go back and watch the probability lecture. Okay, so now I just need to go through and actually fill in the relevant bit of information. So let's first of all find the probability of passing the reading test given somebody's already failed the listening test. So we're given the fact they failed the listening test, the probability of passing the reading test, that's 50%. So that probability there should be equal to 50%. Okay. Let's find the next probability. So what's the probability of failing the listening test? Well, the probability of failing the listening test, that's a 40% chance of that happening. Okay, so we're going to multiply that by 40%. Okay, then I'm going to divide by the probability that they pass the reading test. Well, the probability they pass the reading test, I've calculated that in that last example, that's equal to 32%. So the last question gave me 32%. So when I stick all of these numbers into a calculator, I find this comes out as about 63%. It's 62.5%. Okay, fantastic. So let's have a look at question 7 then. So question 7 says, a competition is being run to see who can eat a sandwich the quickest. 120 people take part. So I'm going to underline that because that might come handy later. So 120 people take part. The times of the participants are found to be normally distributed with a mean of 30 seconds and a standard deviation of 3. So in other words, if I define my random variable x as the time taken to eat a sandwich, okay, so time to eat sandwich, then I'm told that this random variable x, should be normally distributed with a mean of 30 and a standard deviation of 3, which means the variance, which remember is the parameter that goes in the second position, in this course at least, is 3 squared, or 9. So I need to find an estimate to the nearest integer for the number of people who ate a sandwich in 26 seconds or less. So in other words, I want to find the probability, first of all, of picking somebody out, okay? So what's the proportion? What's the probability that x, the time taken to eat the sandwich, is less than 26, okay? So it's 26 seconds or less, so I guess it should be less than or equal to. Of course, it's continuous, so it doesn't matter whether it's less than or equal to anyway, okay? So first things first, let's check. It's a less than or equal to situation, which means I can just get away with using the tables, okay? So I don't need to do a conversion. If I was dealing with greater than, I need to do 1 minus. It's a less than situation. I'm using the tables which deal with less than situations, they're cumulative probabilities, so I'm fine here. So my first task is to standardize. My first task is to basically take this 26 and say, how many units of standard deviation from the mean does 26 lie? So in other words, to standardize, I'm going to do z is equal to this 26. I'm going to take away the mean, which is 30, and divide by the standard deviation, which is 3. So if I do that, if I do 26 minus 30 divided by 3, I find that that comes out as negative 1.33. So in other words, 26 lies about 1.33 units of standard deviation below the mean of 30. Okay. So therefore, all I need to do is look up on the tables the probability of z. So remember, z is a distribution with a mean of 0 and a standard deviation of 1. Okay. Find the probability that I obtain a value less than or equal to 1.33 units of standard deviation from the mean. So I need to pull up my tables in order to do this. So if I pull up my tables, I'm looking for negative 1.33. So I'm looking at negative 1.3, which is this row, and I move across to the 0.03 column, which is this column here. So that's going to give me negative 1.33. I find the intersection point, which is going to be 0.0918. So that's the probability. Okay, so there's a 0.0918 chance. Okay, you could write that as 9.18% chance. Okay, so 0.0918 is the probability, or 9.18%. Okay, but just be aware that that's not quite the end of the question, because I need to find an estimate for the number of people who ate a sandwich in 26 seconds or less. So I know the proportion of students is 9.18%, or the proportion of people is 9.18%, okay? That's the probability of obtaining somebody who eats a sandwich in 26 seconds or less. So I know that 120 people take part. I'm told that in the question. So I basically know that 9.18%, about 9% of people eat a sandwich in 26 seconds or less. There's 120 people, so all I need to do is basically find out what is 9.18%, or 0.0918, depending on what you want to use, times by my 120. What is 9.18% of 120? Well, if I do that, it comes out as about 11 people. Okay, it comes out as about 11 people. And it says to the nearest integer. Okay, a nearest integer, obviously you can't have 0.1 of a person. Okay, so 11 people is what we're looking at there. Okay, fine. Let's have a look at part 2. So Harvey knows that 31% of people ate the sandwich in a longer time than he did. How long did Harvey take to eat the sandwich? Give your answer to the nearest integer, or the nearest second. Okay. So Harvey knows that 31% of people eat a sandwich in a longer time than he did. So if I let Harvey's time be h, I'm basically saying the probability of obtaining somebody with a longer time than Harvey, so if I say x is greater than h, that should be equal to 31%. Now clearly I'm going to be using the tables in just a second, so I need to convert this greater than situation into a less than situation, okay, because of course the tables are cumulative, which means they can only work with less than probabilities. So therefore I'm going to say the probability that x is less than or equal to h should just be 1 minus whatever the greater than probability is going to be, so it should be equal to 69%, okay? So that's the less than or equal to. So in other words, the probability of ending up with somebody who eats a sandwich in a longer time than Harvey is 31%, which means that the probability of finding somebody who eats a sandwich in a shorter time than Harvey did should be 69%. It's just the complement, okay? So first things first, I'm going to find the standardized value, okay? So I'm going to take h and I'm going to standardize it. So I'm going to take z is equal to whatever Harvey's time is, take away the mean, which is 30, divide by the standard deviation, which is 3. Okay. So in other words, I'm going to look up on the tables, and I'm going to try and find the probability in my tables, which corresponds to so h is less than 30 over 3. That's Harvey's time standardized. I'm going to look up in my tables and I'm going to try and find as close as possible to 0.69, okay? Because 69% is 0.69. So let's actually look in my tables and try and find a value which is as close as possible to 0.69. So let's have a look. 0.69, where are you? So I'm going to look in the tables. I'm going to be looking in the bulk of the tables down here. I'm looking for a probability of 0.69. So I think that's probably the closest value I can find, which is 0.50. Okay, so 0.50. So in other words, I'm basically saying that h minus 30 over 3 should correspond to 0.5 units of standard deviation from the mean. Okay, so therefore all I have to do is solve this equation here to find out what Harvey's time is. Okay, so if I solve this equation, I basically find that Harvey's time is about 31.5 seconds. Okay, so to the nearest integer, I'm going to call that 32 seconds. Okay, so hopefully that makes sense. All right, let's have a look at part 3. So we have the times of 25 people are randomly selected. Find the probability that the mean time of these 25 people is 29 seconds or less. Okay, fine. So I'm basically saying that I'm selecting 25 people now. So I end up with a sample from the original 120 who did this experiment or did this competition. So I'm basically saying now, if I take the mean time of these 25 people, the mean time of my sample, it's still going to be normally distributed. Okay. However, the mean is going to stay the same, so the mean is going to be the same as before, which is 30, but the variance is going to decrease by a factor of n. In other words, my 3 squared, which is my variance, is going to decrease by a factor of 25. That's the size of my sample. This is just the central limit theorem, okay? Because I'm now dealing with a sample, and it's got a sample of 25 people, I know that my distribution should effectively become more peaked. Okay, so my distribution should become better approximated to what the true population is doing. In other words, the variance should decrease, and it should decrease by a factor of n, but it becomes more centered around the true mean value. Okay, so I need to basically now find the probability that the mean time of these 25 people is 29 seconds or less. So in other words, it's less than or equal to 29. Okay, so first things first, I'm going to standardize. I'm going to find how many units of standard deviation does 29 lie away from the mean. So I'm going to take my 29, I'm going to take away my mean value, and I'm going to divide by my standard deviation. Now remember, I'm using the parameters from my sample mean, so my mean of my sample, okay? So therefore my standard deviation, I guess I should call it standard error because it's talking about the mean of a sample rather than one individual observation, should be equal to the square root of 3 squared over 25. Well, that's just equal to 3 over the root of 25, okay? So therefore, I find that 29 lies about negative 1.67 units of standard deviation from the mean. So in other words, all I need to do is look up in my tables and find the probability of obtaining a value which lies less than or equal to 1.67 units of standard deviation from the mean. So let's do that, okay? So I'm going to look up in my tables. I'm going to look at negative 1.67. So let's find negative 1.67. So there's negative 1.6. Move across the 0.07 column, find the intersection point. So let's see, the intersection point is there. That's going to come out as 0.0475. Okay, so 0.0475. So 0.0475. Okay, so the probability that somebody the mean time of these 25 people is 29 seconds or less is about 4.75%. There's your final answer. Okay.
All right, fine. So let's have a look at the last question, which is question 8. So we have 2 classes sitting a test. We're told that a sample of 14 test papers from class A is found to have a mean mark of 46 with a standard deviation of 4. So I'm going to write this down. Okay. So for class A, we have 14 test papers. So I'm going to say N1 is equal to 14. Okay. The mean mark of these 14 test papers, so X1 bar, is equal to 46. And the standard deviation of these of this sample is 4. So sample standard deviation, which I'm going to write as S1, is equal to 4. Okay. Now we're also given similar information for class B. So I'm going to write this down. So for class B, we have the sample size, so N2 is equal to 11. We have the mean mark, so X bar 2 is equal to 44. And the standard deviation of this sample, so S2, is equal to 2. Okay. For part 1, for A part 1 at least, we're asked to construct a 95% confidence interval for the difference in the population mean marks of the 2 classes. In other words, when I look at the population mean marks, so mu1 take away mu2, I'm looking for a difference between the population mean mark of class A and the population mean mark of class B. Okay? I'm basically saying if I'm going to construct a confidence interval, I can use these sample means, so x1 bar take away x2 bar. Okay? Look for the difference in them, and then basically allow a little bit of a margin of error to basically include 95% of my data. Okay, so because I want to include a 95% symmetric confidence interval, I'm basically saying include 95% of my data. I've got my difference in my sample means, include 95% of my data, okay, and then I can be 95% sure that the difference in my population means should also lie within that range, okay, or within that interval. So let's first of all find the value of m. Okay, so to find the value of m, I'm going to basically first of all find how many units of standard deviation I need to consider in order to include 95% of my data. Well, first things first, I need to figure out what distribution I need to sample from. So look, because I asked myself 2 questions. First of all, is N1 and N2 greater than or equal to 30? Okay, so have I got a big enough sample size? That's the first question I asked myself. The second question I asked myself is, do I know the population standard deviations for both sigma 1 and sigma 2 for both samples? Okay, so if the answer to the first question is yes, I ask that question. If the answer to that question is yes, I use the Z distribution. If the answer to the second question is no, I use the T distribution. If the answer to the first question is no, I use the T distribution. So just remember, this is fairly standard stuff. We've done it enough times now. Okay, ask myself 2 questions. First of all, sample size. Is it greater than or equal to 30? Second question, do I know the population standard deviation for both of my samples? Okay. If the answer to both those questions is yes, I can use the Z distribution. Otherwise, for safety, I'm going to use the T distribution. So in this case, the answer to both those questions is actually no. So therefore, I'm going to use the T distribution. So remember, the T distribution has an extra parameter, and the extra parameter is degrees of freedom. And just remember that degrees of freedom is given by the first sample size, add the second sample size, take away 2. It's basically the degrees of freedom for the first sample, add the degrees of freedom for the second sample. Okay. So therefore, in that case, N1 is equal to 14, N2 is equal to 11, 14 plus 11 is 25, take away 2, that's going to give me 23 degrees of freedom. Okay. So let's first of all find, I'm going to be using a T distribution. Let's first of all find the critical value associated with 23 degrees of freedom on my T distribution that gives me a 95% confidence interval. Okay. Then I'm going to multiply that by my standard error. Well, in this case, I'm just going to calculate the standard error as the standard deviation for the first sample squared divided by N1 plus the standard deviation for the second sample squared divided by N2. Okay, and then square root all of that thing. So let's go ahead and actually calculate these values. Let's first of all find the critical values. Let's first of all find how many units of standard deviation I need to consider each side of the sample means in order to include 95% of my data. So I'm going to bring up my tables. Okay, so I'm going to bring up my T tables, which are all the way down here. And I'm looking at a confidence level of 95%. So that's the one I want. And I'm looking degrees of freedom as 23. So I'm looking in this row, and I'm looking for the intersection point of this row and this column. That's going to be my 2.069. Okay, so 2.069 is basically how many units of standard deviation I need to consider each side of the mean, so positive direction and negative direction, in order to include 95% of my data.
And then going to multiply that. Well, let's actually fill in the data here. We've got 4 squared over 14 plus 2 squared over 11. And I'm going to square root all of that. Okay, so let's see there. So if I stick all of that into my calculator, I basically find out my margin of error is 2.54. So I'm basically going to take the difference in my sample means, okay, and I'm basically going to add and subtract 2.54 from that, and that's my confidence interval. So let's do that now. So first things first, the difference in my sample means, okay, should just basically be x bar 1 take away x bar 2. Now notice the order which I'm doing it in, okay? I want to find the difference between mu1 and mu2. If I wanted to do mu2 take away mu1, I need to make sure the difference in my sample means was consistent as well, okay? But I'm doing mu1 take away mu2, okay? So in other words, I first of all need to find the difference in my sample means. So x bar 1 take away x bar 2. Well, I can do that really easily. It's just going to be 46 take away 44, okay? So that's going to leave me with 2. So I'm going to end up with 2, take away my margin of error, which is 2.54. That's my lower bound. And the difference in my sample means, sorry, my population means, so mu1 take away mu2, should be between, well, again, x bar 1 take away x bar 2 is 2, plus my margin of error. Okay? So in other words, my final confidence interval, so I'm just going to squeeze it in down here, is going to be negative 0.54 up until 4.54. Okay, so basically my difference in my sample, a difference in my true population means at 95% confidence level should lie between negative 0.54 and 4.54. Now, of course, if you decided to do your difference in the population means the other way round, in other words, mu2 take away mu1, then it should be between negative 4.54 and 0.54. So just be the negative of what I've got here. Okay. Now for part 2, we need to interpret what the confidence interval shows. We'll have a look at this confidence interval. Because it's a difference in the population means, what I'm basically saying is that I can be 95% sure that the difference in my population means, so mu1 take away mu2, should span 0. Because have a look, the lower bound is negative and the upper bound is positive, which means the difference in my population means should span 0. In other words, I can say that mu1 take away mu2, because it spans 0, I'm just going to write equals 0, or it's approximately equal to 0, okay? Which then means I can imply there that mu1 should be equal to mu2. So I can basically say at the 95% confidence interval, sorry, 95% confidence level, okay, that there is no difference in the mean marks of the two classes. Okay? Right? And the reason being is because I've shown that 95% confidence level, the difference in the sample, the difference in the population means span 0, which means just rearranging this, so rearranging the fact that they span 0, I get the fact that mu1 should be approximately equal to mu2, okay? Which means at 95% confidence level, mu1 should be equal to mu2, which means there's no difference, okay? So mu1, the population mean of class A, is equal to the population mean of class B, which means there's no difference in the mean marks, okay? All right, fine. So let's finally look at part B of question 8. So this now says, using the same data which we used before, so I'm just going to pull across the statistics we've been given. And of course, I know that I'm going to be using a t-distribution with 23 degrees of freedom, okay? Then I'm basically being asked now to do an actual hypothesis test. The last question was about confidence levels using this data. Now I'm going to be using significance levels. So I'm going to be using hypothesis testing. So I need to test at the 10% level of significance. So my level of significance, alpha, is equal to 10%. Whether there is enough evidence to suggest that class A performed better on average than class B. So let's write down my hypotheses, okay? So first of all, my null hypothesis is saying that there is no difference. So mu1 is equal to mu2, okay? And in these types of questions, you always assume that there's no difference in the population means, okay? However, my alternative hypothesis, well, let's have a look. The wording of the question will help you out here. So I need to suggest that class A performed better on average than class B. In other words, the average mark of class A, which I'm writing as mu1, should be better, so greater than, mu2. Okay, so the average mark of class B. So that's my alternative hypothesis. Now from this, are you happy that because I'm looking at a greater than situation, I can basically infer from this that it should be a right-tailed test, okay? Now clearly, if it was a less than situation, if I was looking at the case when mu1 was less than mu2, then I'd be looking at a left-tailed test, okay? And if I was looking at a not equal to, so not being the same, I'd be looking at a two-tailed test. But in this case, it's greater than, so it's a right-tailed test. So if I make a quick sketch, so here's my curve, okay? I'm basically saying at the moment that mu1 should be equal to mu2. That's my null hypothesis. This is what I'm going to assume is true. And I'm basically going to say, well, okay, what's the probability of obtaining this particular sample data if that null hypothesis was true? Okay. And because it's a right-tailed test, what I'm interested in is what is the probability that I end up in this critical region up here. Now, the size of this critical region should include 10% of my sample, or 10% of my data, okay? Because my significance level is 10%, which means I'm going to be significant 10% of the time, okay? So first things first, I need to find what this critical value is. Where's the cutoff point? Where's the point where I start to say, the probability of obtaining this sample data is low enough that I can actually say this null hypothesis is probably not going to be correct, okay? So first of all, I need to find my critical value. So I need to look on my tables, okay, and I'm going to be using a t-distribution because I established that in the last part, okay? I'm going to be using a t-distribution with 23 degrees of freedom, and I need to find my upper tail probability of 10%. So let's have a look at this. So let's pull up my tables. So here are my tables here. I'm going to be looking at my upper tail probability, so I'm going to be looking along the top, for 10%. So there's my 10%, and I'm looking for 23 degrees of freedom. Let's find the intersection point. So the intersection point should be 1.319. Okay, so that's how many units of standard deviation from the hypothesized mean I'm allowed to lie before I start to reject the null hypothesis. So that was 1.319. That's my critical value. Okay. So basically, if I basically now need to go ahead and calculate my test statistic. Now, my test statistic actually asks the question, well, how far from the hypothesized difference in the means does this sample data lie? If it lies more than my critical value of 1.319, then I know that I can go ahead and reject the null hypothesis. I can say, well, actually, it's probably not going to be likely that this sample data will come up. So let's check this, okay? So let's calculate my test statistic. So my test statistic will be given by, well, let's check it, okay? My test statistic will be given by the difference in my sample means, so 46 take away 44, which is 2, take away the hypothesized difference in my means. Well, if mu1 is equal to mu2, if I take them away from each other, that should just come out as 0, okay? So I'm taking away 0 there. Divided by, well, in this case, I'm just going to do the square root, so I'm going to do standard error, which is going to be the square root of s1 squared, which is 4 squared, over n1, which is 14, plus s2 squared, which is 2 squared, over n2, which is 11. Okay, so if I stick that in my calculator, I get a test statistic of 1.63. Okay, so basically what I'm saying then is that if this null hypothesis was correct, if there genuinely wasn't a difference in the population means of these two classes, then this sample data should lie 1.63 units of standard deviation away from the difference in my sample means, which is 0. Okay, so basically that's about a difference of about 1.63 units of standard deviation from my hypothesis. Okay, so because 1.63 lies all the way out over here, so 1.63, my test statistic of 1.63 lies all the way out over here, I lie in the critical region, which means that I know that I'm probably going to be rejecting the null hypothesis because I fall in that critical region. I fall in the region where I say, actually, I'm not happy that that is a high enough probability to obtain this sample data. Okay, so it lies far enough away from the hypothesized difference in the means to say it's probably not the case that this is true anymore. But just to be sure, I'm also going to calculate the p-value as well. So just remember that the p-value is basically the probability of obtaining this sample if the null hypothesis is true, or obtaining a more extreme sample. So let's check this. What do I mean by more extreme? Well, basically more extreme lies further away from the hypothesized difference in the means. So here's the hypothesized difference from the means, it's in the middle. Here's my test statistic at the moment. So I basically need to work out, well, what's a more extreme value than that? So more extreme lies further away from the null hypothesis, so it lies further to the right. Because clearly, if I move to the left, I'd be moving closer to this value, okay? But because I move to the right, I want to move further away. So in other words, I want to find the probability of obtaining a value on my table, so write t, which is greater than or equal to 1.63. That's going to be a more extreme value. Okay, so let's go ahead and actually look on our tables and see if we can find that. So again, I'm going to be looking at degrees of freedom, which is 23. So I'm still going to be looking in this row here. Okay, but this time I'm going to try and find as close as possible to 1.63, which is my test statistic, and I'm looking beyond that, okay, because it's an upper tail probability. So 1.63 is going to lie between these two values here. Now, in all honesty, I'm going to take this value, so the 1.714, which corresponds to an upper tail probability of 5%, on the basis that 1.63 is slightly less than that, which means that 1.73 lies even further, so it's even more extreme. So I can be confident that my upper tail probability is going to be slightly more than 5%, so I'm just going to say it's 5% instead. Okay, so in other words, my p-value should be equal to about 5%. Okay. So those are my test statistics, that's my p-value. So I know that I'm going to be rejecting the null hypothesis. By the way, I can also work out that I'm going to reject the null hypothesis for my p-value because my p-value is less than my level of significance. Okay, so because I'm basically saying, I'm saying that if the probability of obtaining this sample data is 5%, which is what I've worked out as the p-value, and I'm basically allowing anything above 10% to be not significant. So I'm basically saying anything below 10%, that's a significant sample. This is below 10%, it's 5% probability, it's less than the 10% cutoff, which I'm allowing. So therefore, I can say it's significant. Okay, so I've got to actually put this into words now. So I'm going to say, since the test statistic of 1.63 lies further into the critical region than the critical value of 1.319, so that's what I calculated. And so I'm also going to write this in as well. I'm also going to refer to the p-value, okay? The p-value of 5% is less than the level of significance, which is 10%. Then, so I'll write this in, I'll underline my joining words because I think it's nicer to see it like this, so I can basically break it up and chunk it up into sections. Then we reject the null hypothesis. Okay, that's not enough. I still need to put this into context. I still need to talk about the marks of the two classes. Okay, so I can say, thus, there is evidence at the 10% level of significance to suggest that, well, now I need to go back, so I need to look mainly at my alternative hypothesis. I'm not saying this is true, I'm just saying that there's enough evidence to reject this null hypothesis, okay? And remember that I was after a difference in the two classes. So remember, mu1 represents the mean mark of class A, and mu2 represents the mean mark of class B, okay? So I can basically say that at the 10% level of significance, to suggest that class A performs better on average than class B, okay? So notice the tone of language which I'm using. I'm using fairly neutral language. I'm not saying anything is definitely true. We never accept anything, so I'm not saying anything is definitely true. I'm just basically saying, well, look, these are my reasonings, okay? So first of all, test statistic lies further into the critical region than the critical value, okay? Second reason, the p-value of 5% is less than 10%, the significance level of 10%. So I have two pieces of evidence to basically say, well, look, according to this particular sample data, we can reject the null hypothesis.
Okay, but then I go on to say, and I say, well, look, according to this evidence, okay, so I'm not talking about things in general, I'm saying this evidence, the thing which is in front of us at the 10% level of significance. I'm actually quoting how significant I've made my sample, okay, so 10% level of significance. I can suggest, based on this evidence and this significance level, that Class A performs better on average than Class B. I'm not saying it definitely does, I'm just saying, based on what's in front of me, I'd suggest this is probably a good conclusion to make. Okay, but hopefully that makes sense. We've answered the question, okay, and it's nice and clearly laid out. Okay, so first of all, I lay out my data, my statistics, work out whether it's T distribution or Z distribution. Secondly, null hypothesis and alternative hypothesis. From that, I work out what type of test I'm going to use, right-tailed, left-tailed, or two-tailed. Then I calculate test statistic, p-value, work out where my test statistic lies. Does it lie in the critical region? Work out my p-value, then do a nice little conclusion, and that's as easy as it comes. Okay, so hopefully that makes sense.